Ever wondered how machines predict house prices, stock trends, or even the weather? It all starts with regression models. These algorithms don't just crunch numbers, they uncover patterns that shape our world. Welcome to day 16 of the 30 Days of Machine Learning series. If you're just joining, don't worry. You can click right here to access the full playlist and catch up on every step of the journey so far. And hey, make sure to hit that subscribe button so the next video in this series drives straight into your feed. In this video, we'll unravel the magic of regression models like linear regression, gradient boosting, random forests, and XGBoost, applying them step by step to real-world data. You'll learn pre-processing, visualization, and model evaluation, all you need to master predictive modeling and choose the best algorithm for your dataset. Let's dive in. Here we go, loading the essentials: pandas for data manipulation, NumPy for numbers, and some visualization tools to bring it all to life. Loading the dataset and peeking at the first few rows to get a glimpse of what we're working with here. Checking the dataset's dimensions, understanding the column names, and then getting a quick overview of the data's stats. First, we check for missing values. Then, we drop any rows where the price column is missing and recheck. Let's grab all the numeric columns from the dataset. These are the ones we'll likely work with for analysis or modeling. We're applying the simple imputer to handle missing numeric values, filling them with the median of each column. This step ensures the dataset is clean and ready for further analysis without losing valuable information due to missing values. Let's identify the categorical columns in the dataset. These are typically non-numeric and hold important qualitative information. We're applying Label Encoder to convert categorical values into numerical ones. This transformation makes the data suitable for machine learning models, turning labels into numbers while preserving the relationships between different categories in the dataset. Plotting the distribution of price using a histogram with a KDE overlay. This gives a clear picture of how the price data is spread out. Generating a heat map to visualize the correlations between numeric features. This helps spot relationships and potential patterns across the dataset in a glance. Plotting a scatter plot to visualize the relationship between the number of rooms and the price. This shows how they might be connected. Creating a scatter plot to explore how price varies with distance. This visualization helps us understand the potential impact of location on pricing. Here's a box plot to compare the price distribution across different regions. It's a great way to spot regional trends and outliers. Visualizing the distribution of land size with a histogram and KDE. This helps us understand how land size is spread across the dataset. Splitting the data into features, X, and target, Y, with price as our prediction target. Checking the shapes of X and Y to ensure correct sizes. Splitting the dataset into training and testing sets, reserving 20% for testing. This ensures our model is evaluated on unseen data, helping us gauge its real-world performance. Checking the shapes of the train and test sets to confirm proper splitting of the data. This ensures everything is aligned and ready for model training. We're scaling the features to ensure consistency. The standard scaler normalizes the data, making the model training more efficient. The training set is fitted, and the test set is transformed accordingly for consistency. Importing MSE, R-square, and MAE to evaluate the model's performance and prediction accuracy. We're defining a function to streamline model evaluation. The function fits the model on the training data and uses it to predict the test data. Then, it calculates essential performance metrics such as mean squared error, MSE, mean absolute error, MAE, and R-square score, which give insights into prediction accuracy and model fit. We also compute accuracy as a percentage to understand how well the model performs overall. Finally, the function prints out the model's name and all these metrics, helping us evaluate how well the model is generalizing to new, unseen data. Creating an empty list to store results from different models. We're initializing a linear regression model and passing it through the evaluation function. This will give us performance metrics like accuracy for the linear regression model. Appending the results of the linear regression model to the results list, storing the model name and its accuracy for later comparison with other models. We're initializing a gradient boosting regressor model with a fixed random state, then evaluating its performance using the previously defined function to assess its accuracy and other metrics. Appending the results of the gradient boosting regressor to the results list. We're initializing a random forest regressor model with a fixed random state, and then evaluating its performance using the evaluation function to see how well it predicts on the test set. Appending the random forest regressor's results to the results list, including the model name and its accuracy for comparison with other models we've tested. We're initializing an XGBoost regressor model with a fixed random state, then evaluating its performance using our model evaluation function to see how it performs on the test data. Appending the XGBoost regressor results to the results list, including the model name and its accuracy. Creating a data frame from the results to compare model accuracies easily. Here's the model performance summary, sorted by accuracy. The XGB regressor leads the list, outperforming other models with the highest accuracy, making it the most effective for this dataset. That's a wrap on regression models. We've covered everything from pre-processing to model evaluation with linear regression, gradient boosting, random forest, and XGBoost. But we're not stopping here. In the next video, we'll explore the fascinating world of unsupervised learning. Curious about clustering and more? Click on the screen to continue, and let's keep this learning journey going.